Now, wait a minute. I want you to think about something peculiar. You burned a letter last week. Love letter, text documents, whatever it was. You watched it turn to smoke and ash. Gone forever. Right. The words, the ink, the paper, all destroyed. Except here's the thing that will keep you up tonight. According to the laws of physics, that letter still exists. Every single word, every curl of every letter. It's all still there in principle. The universe hasn't forgotten a single thing about it. Sounds crazy, doesn't it? But by the end of our time together, you're going to understand exactly what I mean. You're going to see why the past isn't really gone at all, and more than that. You're going to understand something profound about the nature of time itself. Something that most people, even many scientists, never quite wrap their heads around. Let me start with something simple. Something you can see with your own eyes tonight if it's clear outside. Go look at a star. Any star. Pick one. Now. Here's a question that seems almost too obvious to ask. What are you looking at, you might say? Well, I'm looking at a star. Feynman. What kind of question is that? But you're not looking at a star. Not really. You're looking at the past. See? Light travels fast. About 186,000 miles every second. That's quick enough to zip round the Earth 7.5 times while you snap your fingers. But space is big. Really, really big. The nearest star to our sun, a little fellow called Proxima Centauri, is so far away that its light takes 4 years to reach us. 4 years. So when you look at that star tonight, you are not seeing what it looks like now. You're seeing what it looked like 4 years ago. You're literally looking backward in time. And it gets better. You know the North Star, Polaris, sailors, had been using it to navigate for centuries. That light started traveling toward Earth about 430 years ago. When that light left Polaris, Shakespeare Snots was writing plays. The Pilgrims hadn't landed at Plymouth Rock yet. That ancient light carrying news from the past is just now arriving at your eyeball. But we're just getting started. Consider, Dan, that bright star at the top of the Northern Cross, beautiful blue-white thing. Its light has been traveling for about 1,400 years. When that light started its journey, it was around 620 AD. The Roman Empire had fallen. The Vikings hadn't started raiding yet. And here you are catching those ancient photons in your eye. Reading a message from the past. Now think about the Pleiades. That lovely little cluster. The Seven Sisters. Their light left about 440 years ago when Queen Elizabeth I sat on the English throne. And the Hercules cluster. That faint fuzzy patch you can barely see, its light, started traveling during the last ice age 23,000 years ago. Your ancestors were painting caves in France. The Andromeda Galaxy is even more stunning. On a clear night, away from city lights. You can see it as a faint smudge in the sky. It's the most distant thing you can see with your naked eye. The light from Andromeda has been traveling for 2.5 million years to reach your eyeball. 2.5 million years. When that light started its journey, there were no humans on Earth. Our ancestors were just figuring out how to chip stones into tools. We call them Homo habilis. They had brains about half the size of ours. And yet that ancient light carrying information from millions of years ago is streaming into your eye right now. So here's the first thing I want you to understand. The past is constantly arriving. It's not gone. It's traveling toward us at the speed of light from every direction. Now, think about what this means. Every direction you look, you're seeing a different time. Look at your hand and you're seeing it as it was a billionth of a second ago. Look across the room. Maybe a 100 millionth of a second ago. Look at the moon and you're seeing it from about 1.3 seconds in the past. The sun. That's 8 minutes ago. Jupiter, when it's close, about 40 minutes. Saturn, over an hour. You're swimming in the past right now. Every photon hitting your eye is a little messenger from history. Some of those messengers left home minutes ago. Some left centuries ago. Some left before the Earth existed. And they're all arriving at the same moment right now. Bringing you news from across time. Here's something strange to think about. Suppose the sun suddenly disappeared, just vanished. How long before we'd know? 8 minutes. For 8 minutes. We'd see the sun hanging there in the sky, feel its warmth, have no idea anything was wrong. Then 8 minutes after it disappeared, the last light would reach us and the sun would blink out. And at that same moment, we'd start falling because gravity also travels at the speed of light. The universe doesn't update instantly. It updates at the speed of light, and that means you're always looking at the past. The present is invisible. By the time light from anything reaches your eyes, that thing has already changed. The universe is a time machine, and you're riding in it. But that's just the warm-up. That's just the appetizer. Now, I want to tell you something deeper. Something about the laws of physics themselves. Take Newton's laws. Beautiful laws. Simple laws. A ball rolls across the table and Newton tells you exactly how it moves. Force equals mass time acceleration. Elegant. But here's something Newton noticed and it bothered him a little. His equations don't care which way time goes. Let me show you what I mean. Imagine I film a billiard ball rolling across a table, bouncing off the cushion and coming back. Now I play the film backward. What do you see? A billiard ball rolling across the table, bouncing off the cushion and coming back. Could you tell which version was forward and which was backward? No, both versions look perfectly natural. Both obey Newton's laws exactly. Try it with two balls. Film them colliding. One comes in from the left, hits the other. They both go off at angles. Now play it backward. Two balls come in at angles, collide. One goes off to the right, still perfectly legal. Still obeys all. The laws of physics. You can't tell which way time is supposed to go. Try it with a pendulum. A weight swinging back and forth. Film it. Play it backward. Still a pendulum swinging back and forth. The physics works either way. This is what physicists call time reversal symmetry. The laws of motion work just as well running backward as forward. If you film any simple mechanical interaction, the movie played in reverse shows another perfectly legal event. The physics doesn't know the difference. Now, let me be more precise about this because precision matters. When I say time reversal, I don't just mean running the movie backward. I mean reversing all the velocities. If a ball was moving left, now it's moving right. If it was spinning clockwise, now it's spinning counterclockwise. You flip all the motions, and then the equations work perfectly going the other way. Asterisk the technical way to say this. Newton's second law F equals ma involves the second derivative of position with respect to time. The second derivative that means the equation contains t terms and t equals t. The sign of time doesn't matter. The equation is the same whether time runs forward or backward. Now, you might say, Feynman, that's silly. Of course, I can tell which way time goes. Eggs break. They don't unbreak. Coffee cools down. It doesn't heat up by itself. Perfume spreads through a room, but never collects back into the bottle. A glass falls off the table and shatters. The pieces don't spontaneously jump back together. You're absolutely right. But here's the puzzle. The laws governing every single atom in that egg, every molecule in that coffee, every particle in that glass, those laws are time symmetric. They work perfectly fine in both directions. So why do eggs break, but never unbreak? This is one of the deepest questions in all of physics, and we'll get to the answer. But first, I want to push deeper into what the laws of physics actually say about the past. Let me tell you about quantum mechanics. Now, this is where things get really interesting. In quantum mechanics, the way we describe a particle or a system of particles is with something called a wave function. Now, the wave function is a funny thing. It's not like a regular wave like a wave in water. It's a mathematical object that encodes all the information about the system, everything. Where the particle might be, how fast it might be going, which way its spin is pointing, everything you could possibly know or measure. The key equation in quantum mechanics is the Schrödinger equation. It tells you how the wave function changes over time. And here's the beautiful thing. The Schrödinger equation is also time-symmetric, not in exactly the same way as Newton's laws, but in a closely related way. If you know the wave function now, you can calculate exactly what it will be in the future, and you can calculate exactly what it was in the past. The equation works both ways. This property is called unitarity. Fancy word. What it means is simple. The evolution of the wave function preserves information. Nothing is ever lost. Nothing is ever created. The information just moves round, transforms, rearranges, but it's always there. Think of it like this. Imagine you have a code book that translates between two languages. Every word in language A corresponds to exactly one word in language B and vice versa. Nothing is lost in translation. You can always translate back. That's what unitary evolution means for quantum mechanics. The laws of physics are a perfect translation between the state of the universe at time 1 and the state of the universe at time 2. You can always translate back. Let me try to explain this the way I might explain it to a bright 12-year-old. Imagine the universe is like a gigantic jigsaw puzzle. At every moment, all the pieces are arranged in some pattern. The laws of physics tell you exactly how to rearrange the pieces from one moment to the next. Now, the rule is every pattern can only come from one other pattern. Asterisk, and every pattern can only go to one other pattern. No two different puzzles ever become the same puzzle, and no puzzle ever splits into two different puzzles. What does this mean? It means if you know what the puzzle looks like now, you can figure out exactly what it looked like before. There's only one past that leads to this present. And that past is still contained somehow in the arrangement of the pieces right now. The physicists call this information conservation, and let me tell you, they take it very seriously because if information could ever be truly destroyed, the whole mathematical framework of quantum mechanics would collapse. The equations would become inconsistent. You'd get nonsense answers, probabilities that add up to more than 100%. The universe doesn't allow that. Let me give you an example of how seriously physicists take this for decades. There was a huge fight about black holes. A black hole is a region of space where gravity is so strong that nothing can escape. Not even light. Things fall in and they don't come back out. So for a long time, people thought black holes were the ultimate information shredders. Throw a book into a black hole and it's gone forever. Right? Stephen Hawking discovered something strange in the 1970s. Black holes aren't perfectly black. They slowly radiate energy. They have a temperature. They evaporate over incredibly long times. But they evaporate. A black hole the mass of the sun would take longer than the age of the universe to evaporate. But eventually it would be gone. And here's the puzzle. That radiation seemed to be random. Thermal noise. No information in it. Just heat. So when the black hole finally evaporates completely, where did the information about everything that fell in go? All those books, all those stars, all those unfortunate astronauts, Where did the information encoding their existence go? This bothered physicists enormously. Hawking said the information was destroyed. Other physicists like Leonard Susskind and Gerard Houft said, no, it can't be. If information can be destroyed, quantum mechanics falls apart. They called it the black hole information paradox, and they argued about it for 30 years. That's how seriously they take this, after all that arguing. Most physicists now believe the information does escape. It's encoded in subtle correlations. In the Hawking radiation, it scrambled beyond any hope of practical recovery. But it's there. The black hole didn't destroy the information. It just scrambled it and spit it back out over billions of years. The universe keeps its books. Balanced, nothing is ever truly erased. Hawking eventually conceded the bet. He gave his opponent a baseball encyclopedia because from an encyclopedia, he said information can be recovered it will just like from the universe. So let me come back to that burned letter. You watched it turn to smoke and ash. But think about what actually happened at the level of atoms. The paper was made of molecules. Long chains of carbon and hydrogen and oxygen ranged in complex structures, cellulose mostly. The ink was pigment molecules stuck to those fibers. When you lit the match, you added energy. The molecules started vibrating violently. Chemical bonds started breaking. The paper molecules fell apart and recombined with oxygen from the air. They formed new molecules, carbon dioxide, water vapor, various other combustion products. The ash is what's left, the stuff that didn't fly away. But here's the thing. Every single atom that was in that letter still exists. Not a single one was destroyed. Not a single proton. Not a single neutron. Not a single electron. They just rearranged. They scattered into the air, settled into the ash, spread out into the environment. And the way they scattered, the exact pattern of where each atom went. That pattern is not random. It's determined by physics. It's determined by the exact initial conditions of every atom, every molecule, every photon of heat. The pattern contains all the information that was in the original letter, in principle. And I want to emphasize that, in principle, if you could track every atom that was in that letter, if you could measure exactly where each one went, if you could account for every photon of light and every vibration of every air molecule that interacted with the burning paper, you could reconstruct the letter. Not just that there was a letter, but every word, every flourish of the pen, the exact shade of the ink, everything. The information hasn't been destroyed. It's been scrambled. Asterisk, it's been spread out. It's been diffused into the environment, mixed with trillions of other bits of information. But it's all still there, encoded in the positions and motions of atoms. Now, can you actually do this reconstruction in practice? Of course not. You need to track more atoms than there are stars in the observable universe. You need measuring instruments of impossible precision. You need computers that don't exist and probably can't exist. It's utterly, completely, fantastically impractical. But that's not the point. The point is that the laws of physics don't forbid it. The information still exists. The past is still encoded in the present. It's just hidden, scrambled, but not erased. Let me give you an analogy. Imagine you have a clear glass of water. You carefully place a drop of blue ink in the center at first. You can see the drop. It's distinct, concentrated. Then it starts to spread, diffuse. After a while, the whole glass is a uniform pale blue. The drop is gone. Right? Wrong. The molecules of ink are still in there. They've just spread out. They're mixed with the water molecules. But if you could somehow take each ink molecule, you'd find them all. They haven't disappeared. They've just become very hard to distinguish from the background. Now, The laws of physics say this. If you could somehow reverse the velocity of every single molecule in that glass, water and ink alike, at that exact instant, the ink would undoose. It would collect back into a drop. The movie would run backward and it would be perfectly legal physics. The Schrödinger equation allows it. The laws of motion permit it. We never see this happen because the chances are astronomically small. To reverse all those molecules, you need a ridiculously specific arrangement of velocities. One particular configuration out of an unimaginably vast number of possible configurations. It's not that the laws forbid it. It's that it's unbelievably, inconceivably unlikely. But unlikely is not the same as impossible, and that distinction matters. This brings us to the heart of the matter. Why does time seem to flow in one direction? Why does the past seem gone? If the laws are symmetric, if information is never destroyed, why do eggs break but never unbreak? Why does ink diffuse but never concentrate? The answer has to do with something called entropy. Now, entropy is a tricky concept. People throw the word round, and half the time they don't really know what they mean. Let me try to explain it properly. Imagine you have a box divided in half by a wall with a gas in one half and vacuum in the other. You remove the wall. What happens? The gas expands to fill the whole box. You've seen this. You know it happens. But why? Here's a key insight, and it came from Ludwig Boltzmann in the 1870s. Think about it from the point of view of the gas molecules. Each molecule is bouncing around following Newton's laws, doing its thing. It doesn't know about expanding or filling the box. It just moves. Now, there are many ways the molecules could be arranged in the box. They could all be in the left half. They could all be in the right half. They could be spread out evenly. They could be arranged to spell your name if you looked at them just right. Each specific arrangement of all the molecules is called a microweight. Here's the crucial point. Some collections of arrangements look the same from a big picture view, even though they're different in detail. If the gas is spread out evenly, there are gazillions of different specific arrangements that all look like evenly spread out gas. But if all the gas is crammed into one half, there are far fewer ways to achieve that. Way fewer. Astronomically fewer. Let me give you some numbers. Suppose you have just 100 molecules. How many ways can they be split between two halves of a box? The most likely split is 50 to 50. There are about 100 billion ways to arrange 100 molecules, so you get 50 in each half. But there's only one way to get all 100 in the left half. One way versus a 100 red billion ways. Which do you think you'll see? Now imagine not 100 molecules, but 10 to the 23rd power. That's about how many molecules are in a breath of air. The number of ways to arrange them evenly is incomprehensibly larger than the number of ways to arrange them all in one place. The ratio is a number so big it has more digits than there are atoms in the observable universe. Entropy measures this. High entropy means there are many microweights that all look the same macroscopically. Low entropy means there are few such microweights. When you remove the wall, the gas molecules start bouncing around randomly. They're exploring the space of possible microweights. And because there are so many more microweights corresponding to spread out than to crammed in one half, the gas will almost certainly end up spread out. Not because the laws push it that way, not because there's a force driving it, but simply because there are so many more ways to be spread out than to be concentrated. It's like shuffling a deck of cards. Start with the deck perfectly sorted, hearts in order, spades in order.